So our first speaker is Anders Wallberg from CERN, EPFL, and he will talk about time-dependent integrability from gauge theory. Please, Anders. Yeah.
So let me just make sure. How do I get the pointer? That helped a lot. Yes, perfect. So first, I would like to thank the organizers for giving me this opportunity to give a talk on time-dependent integrability from gauge theory. This is based on a paper that came out last week, plus probably too many works in progress, all done in collaboration with Shota Komatsu, Junichi Sakamoto, and Masahiro Yamasaki. So first, let me tell you why you should care about time-dependent systems. So the fact is that there's many interesting observables in physics that are only accessible to you if you are out of equilibrium. So these are things like transport, thermalization, entanglement growth, the spread of quantum information. And this is only becoming more and more relevant by the day. And this is relevant both in high-energy physics, but also in condensed matter systems. And in the latter case, we've even become increasingly good at engineering such systems. So in condensed matter, they go under names like Floquet systems. There's certain optical lattice physics we can be interested in, quantum circuits. And one take-home message here is that the time is really, it's time to actually study these things seriously. There's interesting questions in theory, there's interesting questions experimentally, and there are not a lot of analytical tools available to you. And that's the gap that we're trying to bridge a bit. So of course, we know that in equilibrium physics, integrability has been a great tool to help us study things analytically. And so that naturally led us to wonder if there is some notion of time-dependent integrability that we can use to compute some of these interesting observables in an analytic regime. Now, we're of course not the first ones to think about this, especially in the math literature. There's actually quite a lot known in various setups, going under various interesting names. But today I will limit myself to studying classical 2D integrable field theories, which have also been studied in a time-dependent manner before, mostly in this context of dimensional reductions of gravity that we just heard about in the previous talk. There was a lot of work done in the 80s, 90s, and also more recently. But I'll study them not because I'm interested in gravity, but just because I'm interested in the two-dimensional system on its own. So here's the outline. First, I will define what I mean by space-time dependent integrability. That's not an obvious notion. Then I'll show you how you can construct examples from four-dimensional Chern-Simons theory, of which you're all now, of course, experts after all the talks today. And time permitting, I will also mention some relations to 3D BF theory, which you can also use to study not 2D integrable field theories, but integrable quantum mechanics, for example. Okay, so first, let me make sure we all agree on what integrability means. So in this context, when I say integrability, I mean that there exists a lax connection, which is built from the fields phi, the couplings h, and it lives on a four-dimensional manifold, which is my two-dimensional space-time times some spectral parameter plane that I'll call C. And the coordinates on C will be this Z here. And it's constructed in such a way that the equations of motion of the theory are encoded in the flatness condition on this connection. And why is this? Does this have anything to do with integrability? Well, you can use this lax connection to construct conserved charges. And that's, maybe the one thing we all agree integrability is related to is some notion of having a lot of conserved charges. It also is related to solvability, because we can then use the so-called auxiliary linear problem to set up some inverse scattering method to actually construct solutions of the theory. Now, I'll not go into detail how that works in practice, but we just need to know that having this kind of auxiliary linear problem is sufficient. And so now we will wonder if we can extend this notion to the time, or more generally space-time dependent regime. So throughout this talk, I will shift between these two notions somewhat freely. So we take our couplings HI, we now want to promote them to functions of time and space. I add little hats to denote that. And it's not even obvious what the definition of integrability should be here, because before we said something like we have a lot of conserved charges, but of course, once your couplings are time dependent, you will in fact have generically no conserved charges. Not even the energy is conserved in these systems. And so it might be even surprising that you can even define integrability here. But luckily, what was found in this context of gravity is that the inverse scattering method can survive. So let's see what that looks like. I will define a system to be a space-time dependent theory to be integrable if, again, the equations of motion are encoded in some flatness condition of some covariant derivatives. But the covariant derivatives I'm using, that's again why I have these hats, they don't only have the light cone derivatives and the lax connection, but they also include some spectral derivatives with certain functions f plus minus appearing in front. And so if you want to show that a space-time dependent theory is integrable, you need not only to find a lax connection, you also need to find these functions f plus minus. So that might sound a bit harder. We'll see in a second a simple example where we can do it. I should note that previously the lax connection only depended on the space-time because it was built from the fields. And now that's no longer true because it's now explicitly built also from the coupling constants, and they are themselves space-time dependent. Again, this means that you don't have conserved charges in this system, also because this flatness condition is modified. But because these covariant derivatives still commute, we do have an auxiliary linear problem, and we do know how to construct soliton solutions in general from a given seed solution. By the way, this is slightly different from what Mir had in the previous talk. He would have had a normal flatness condition, but some more complicated spectral parameter dependence. But okay, this is my working definition. If you have a better definition, I'm more than happy to hear it. But certainly this gives us the solvability we might be interested in. So let's see how this works in practice. Let's take everybody's favorite integral sigma model, the principal-Child model. I make it space-time dependent. That means that I take the coupling here and I make it a function of both time and space. And then I ask for what functions h hat is this model still integrable. So again, that means that I have to cook up a lax connection. I choose this one. I, through some divine inspiration, also cook up these functions f plus and f minus. And I find that the system is integrable if and only if my coupling constant, which is not really a constant here, is satisfied a wave equation. So it should be the sum of a chiral function plus an anti-chiral function. Yeah. Mm-hmm.
Did you relate to a coordinate transformation?
Yeah, so there is so you have to do a coordinate dependent coordinate transformation roughly between the two. And so you can trade these f plus minuses for explicit coordinate dependence in your spectral parameter. So for any functions g1 and g2, this theory turns out to be integrable. That's maybe a bit surprising. Furthermore, if you focus on the case where it only depends on time, so now again I will shift back to just having time dependence, you can easily check that the only function that can be written like this, that's only a function of time, is a linear function. And here I introduce this constant kappa, that you can essentially think about as a deformation parameter. So if you send kappa to 0, you're back to your original time-independent undeformed theory. If kappa is small, you're in the adiabatic regime, where everything changes slowly. If kappa is large, you're in the quench regime. But we can take kappa to be any value you want in between. So, and we should also note, and this is kind of trivial here, but if you take the time derivative of your coupling constant, you essentially get the one loop beta function, but where you replaced h bar by kappa. Now that doesn't sound very deep here. I mean, I just have a linear function, I take a derivative, I just get kappa. But as we still see, this is true for all integrable sigma models you can cook up. Okay, now that was a simple example, but it also takes quite a bit of work by hand. So there's some previous work by Ben, Nat, and Akadi where they really pushed this and found many examples of time-dependent integrable models by simply doing some of these things by hand. But I'm not that brave, so I would like to find some unifying principle that might make it easier for me to find such examples. And of course, we know unifying principles for integrable models in general. That's precisely this kind of 4D Chern-Simons theory that we just discussed. And so what we did in this paper was to construct a space-time dependent version of 4D Chern-Simons. And I'll get back to what that means in a second. But first, let me just review what 4D Chern-Simons is in, basically 2 or 3 slides. So again, it's has this 4-dimensional action. It's a theory on your 2-dimensional space-time times the Riemann surface that you can see here. It contains this one form omega, which is non-dynamical. So you should not vary with respect to omega. You should only vary with respect to the gauge field A. And then once you compute the variation of the action, you find 2 terms. You find a boundary term that you need to set to 0, basically by imposing boundary conditions on A. And you find a bulk term whose equations of motion are basically omega wedge F equals 0, which tells you that if you replace A plus minus by L plus minus, that the equations of motion are naturally the flatness condition on this lax connection. So instead of having to cook up a lax connection by hand, which is generally hard, here I'm going the other way. I start with having a flatness condition, and I now have to find my integrable field theory somehow. And the way you do that is to couple in some 2-dimensional defects. And these come in 2 flavors. You can either add some 2-dimensional defect Lagrangians by hand. Those are called order defects. Everything I say today is perfectly valid for these theories. We checked that explicitly. But given that many people here are maybe more interested in integrable sigma models, for example, I thought it might be more instructive to focus on those. And they come about from a different mechanism in which you include poles in this function omega. So what do I mean by that? You take your 4-dimensional action that we had before, and you take this omega to be not holomorphic, but instead only meromorphic. So it looks like phi of z dz, where this phi is some non-trivial function. And particularly what this does is that phi will have, in general, poles and zeros. I will mark the zeros are these yellow crosses. The poles are some blue dots. And you should think about this as sort of marking some points on your Riemann surface, which will play an interesting role. So the poles act as defects for the gauge field. So in particular, you have to impose boundary conditions at those poles. These could be simple things like saying that the gauge field has to vanish at the poles, or there are more complicated examples. I will basically be agnostic to about what boundary conditions you imposed. But the upshot is that it leads to some edge modes. This is very well known, in particular in condensed matter, that if you have boundary conditions on your gauge field, there will be edge modes living at those boundaries. And similarly, the zeros can play the roles of the poles of your lax connection. So generically, your lax connection will look like this. It will have some simple poles or in general higher order poles at these zeros. And the magic is, and this I will also not show you, is that you can integrate out the Riemann surface. You're left with basically just the marked points, in particular the poles. And that is where your two-dimensional integrable field theory lives. Okay. Now this was all true in the time-independent setup. And we now ask what happens, how can you naturally encode some space-time dependence in this theory? And notice that my four-dimensional coupling constant is basically the one form omega. So all the information about the theory is encoded in omega, plus some information encoded in the boundary conditions that I'll not focus on so much. So the question is, can we somehow make this omega space-time dependent? And again, there was this work of Lewis and Peter Weck that said that indeed you can do this for the principal-Chiral model. And so what we basically did is generalize this to any other integrable sigma model or any other integrable field theory you might be interested in. And the key step is to realize that you can add legs to omega. So before it only had a leg along dz, it was meromorphic. But now I add legs also along x plus and x minus, and I call the coefficients in front of those, I call them psi plus and psi minus. That's just some names. Previously, you could choose phi to be whatever function you want, and different choices of phi give you different integrable field theories and, again, deformations between them. But here you don't have quite as much freedom. So you cannot choose psi plus and psi minus arbitrarily. Instead, you find that if you want to require that d omega is basically a delta function, which is what you needed to impose these boundary conditions that you could make vanish, you need to relate the light cone derivatives of phi with the spectral derivatives of psi. And there are some extra conditions that psi basically has poles where phi has poles, and it has zeros where phi has zeros. Okay? And that you just get from 4D Chern-Simons consistency. But that's all you have to do. So once you do that, you can write down your Lax connection again. You can integrate out your spectral parameter plane, and you're left with a two-dimensional space-time dependent integrable field theory, where, again, the flatness condition is placed by this modified flatness condition, where you had this extra spectral derivative, and these functions f plus minus that I previously had to somehow just engineer by hand are actually related to phi and psi like this. So again, if you want to do this for the principal-Chiral model, you take phi to be this function here that's already known in the literature. You impose this condition on the light cone derivative of phi, and that basically uniquely fixes for you what psi looks like. And then requiring that d plus psi minus is equal to d minus psi plus precisely give you this sort of wave equation on H. So what's happening here is that we had these marked points on our spectral parameter plane. You can forget about phi for a moment, just think about the marked points, which are the zeros and the poles. And all that's happening is that these poles and zeros are now moving as functions of space-time, or in this case, just time, if you want. And what about the relation to Rg that we had for the principal-Chiral model? Well, it carries through completely universally. In particular, if you take phi to just be a function of time, it turns out that the requirements you have to put on psi are so restrictive that there's basically only a one-parameter family of them, function psi, and they're again parameterized by this parameter kappa that controls the strength of the time dependence. And all of this is precisely the same as one-loop Rg flow that we derived in some previous work. So, okay, if you've zoned out for a bit in this 4D Chern-Simons construction, the upshot is that everything I just told you is algorithmic. So if you give me your favorite integrable sigma model, I can construct for you a space-time dependent version of that theory, as long as you can tell me either what the twist function phi is, or if you can tell me what the Rg flow is. And in my last little bit of time, let me just mention, okay. Here, I will not quiz you on this table. This is just to say that here are some of your favorite integrable sigma models. And indeed, we can construct the functions f explicitly. And in my last little bit of time, I'll just mention that you can compactify everything, the spatial direction in the four-dimensional theory. And that leaves you with a three-dimensional theory that is this kind of mixed BF theory. So it's a BF theory plus a Chern-Simons term. Again, we have this parameter kappa. If you send kappa to 0, you have a BF theory, and that's known to give you this Garnier system, also known as the classical Godin model that Benoit, among others, have constructed. But now you have an additional parameter kappa that you can turn on, and that precisely produces for you the space-time dependent versions of, well, here it's really just time dependence because we integrated out x, of those same systems that have already been known in the literature. And you can then study those independently of the 4D Chern-Simons story. And I just want to mention that in the quantum version of that, if you want to solve this, you want to find the eigenstates of that system. So in the time-independent setup, those are just your normal beta states. They're now constructed as these off-shell beta states where you have to integrate over your beta root. And you have this exponential of something that looks like an epsilon divided by kappa, such that if you send kappa to 0, the saddle points are precisely the solutions to your beta equation. So again, here you see some relation between kappa and h bar in that this looks a lot like a path integral, let's say. Okay, but that's some upcoming work. I will not discuss it in more detail. So the conclusion is that we have a way to make integrable field theories in 2 dimensions, space-time dependent, while preserving integrability. There's a very precise recipe for constructing these theories. We can construct basically all of them. So as long as you know how to construct them from 4D Chern-Simons, I know how to make them space-time dependent. Somehow there's a relationship between time dependence and one-loop RG flow. We don't fully understand how that works, but we just observe that it works in every single theory. You can repeat this construction for integrable quantum mechanics, integrable quantum circuits, integrable CFTs. There's a whole world out there for you to study. And in fact, there are many computations that are yet to be done. And I would argue that there's quite a lot of low-hanging fruit. There's many even relatively easy computations that have not been done that are actually interesting physically. And yeah, I don't know how much time I have left. Perfect. Then I'll just say thank you.
Thanks for the very nice talk. Any questions?
I'll just.
Oh, this is really a bit more of a statement on the question, but just you take the attitude of production from 4 dimensions, which are 4 dimensions, you've got a full display. So for us to get down to 2 dimensions, you play any error symmetrism. And I guess you will get it was not translational, then you'll get sentence. To be completely honest, we didn't bother to classify everything. There's plenty to look for just in that process, which will give you manifestly integrable models with nice twisted theory and everything. So that there's actually quite a lot of work to be done there just to do that classification problem. We did it going down to 1 dimensions, and we landed precisely on the Panavic classification. So that was rather neat. You just put in groups, subgroups, and full group, then you get precisely Panavic 1 to 6 for 4 parameters. That's going down to 2 dimensions.
Oh,
that's something to do.
Yeah, that sounds very interesting. I'd love to hear more.
Thank you for the nice talk, but I have a question like, what in practice can you do? For example, can you do the Floquet dynamics with this?
Can I?
Floquet dynamics?
So indeed, you should be able to in this. So I'm a little bit limited here by being classical. So I think many of the good questions you should really ask quantum mechanically. But for example, in this Godin model, you can do exactly something like a Floquet system.
This has been done to a certain extent also in the, I mean, in the quantum version.
Sure.
But in, so maybe other question more suitable for the classical one, can you do, I don't know, just study something in homogeneous potential or things like this? I mean, if I put my fields in some external field, I mean.
Yeah. Exactly something like that I would expect you can do. I mean, one thing that I should mention is that in the classical two-dimensional setup, my time dependence is a bit more constrained. So actually there's something like Floquet where you want to return back to where you were originally is not possible. So it's a little bit less generic, but something like an external potential, I think you can include. Yeah.
Thank you.
So it's a bit related to the previous question. So your motivation had to do with things out of equilibrium and quantum processes. I didn't quite get the procedure that you outlined. Was it for classical integrable models because you were making an example to us right now, or is it basically the extent to which now you can do it?
So in the work we put out last week, it was just about classical. I mean, the motivation was partly that before we study the quantum case, we should really study the classical case first. Partly that once you have done this in 4D Chern-Simons, 4D Chern-Simons is also known to be related to various quantum systems and spin chains and so on. And so now that we understand what is happening, what we should be doing in 4D Chern-Simons, we can now go back to the quantum questions. But indeed, it's true that, and that's why we have many follow-ups, is that I think many of the good questions are really quantum, and that I cannot answer here.
But you expect that it will be possible to study, for instance, quantum lattice models, which can be realized in 4D Chern-Simons, but in a slightly different way, right?
Yeah. So for example, we have these time-dependent integrable circuits. Those we already know how to construct. Spin chains are a little bit subtle, but what you can do something like a time-dependent twist to the spin chain, that's possible. And that's something we are actively working on. So probably classically, the kind of observable you could be looking at though is like, let's construct two solitons and scatter them. And now these solitons are time dependent, but we should still be able to understand the scattering process just using the inverse scattering method. Thanks.
Do you have any model for which you can solve the auxiliary problem, linear problem?
Yeah, so I think for the principal chiral model, people have done this in the context of gravity. There, of course, they're interested in constructing some higher dimensional black hole solutions, but I think you can really make sense of those solitons already in 2 dimensions. We haven't studied it, and probably someone should look at that. I think that would be interesting. Of course, if you go to one of these more complicated 4D Chern-Simons theories, of course, the more poles and zeros you add, the harder it's going to be, but at least in principle, you can do it.
Another question. Could it be that all these time-dependent integrable models come from normal integrable models with more fields, where some of the fields kind of fixed?
So that's a very interesting question. I think I have a backup slide here. Let's see. Somewhere. I have a lot of backup slides, I see. Here, for example. So these models, if you just focus on the time-dependent case, they can be constructed by coupling your integrable field theory to a dilaton gravity theory. So, okay, I guess I should be a bit brief here. Just to say that you add a dilaton, you basically fix the dilaton to be like time. And if you do this in the right manner, the theory will remain integrable and will be exactly like the theories I just discussed. And there's another thing you can do where you do some string theory where you add two extra fields to your worldsheet theory. And then again, you fix how you couple those fields to your matter fields in a specific manner. And then that's known to be related to some exactly solvable, but now time-dependent string theory setups.
Okay, final quick question. And
let me maybe just briefly mention that works for time dependence. I don't think that works for space-time dependence more generally. There, I don't know what you can do.
Yeah, thank you for the nice talk. You talked a lot about time dependence. There is the other choice where you take it just to depend on space.
Yeah.
And then you would have a conserved charge associated to time translations.
Yeah.
Do you see any interesting physics in that case? Or could you, as in not, can you imagine any interesting physics? Or?
Yeah, so I guess you actually studied that in a bit more detail than we did here. I think it's hard to expect that you get too much interesting things here, partly because you're still forced to have these modified derivatives, even if you just have spatial dependence. Roughly what I expect is that it might be true that in this case you have some dt on your charges that vanish because your charges only depend on space, but they will not commute. Here I have roughly the opposite. If I have only time dependence, the charges commute, but they depend explicitly on time. So I don't think you can get some infinite set of conserved charges in either case. But we didn't look at it in much detail.
okay, with that, I encourage everyone to give him more questions after this session, but let's continue to the next speaker. So thanks, Anne.